All right, great. My name is Bernie Bain. I'm a technical marketing engineer with Avere Systems, and we're going to talk about how to use storage in the cloud and what the roadblocks are that you can expect in these types of environments, right? So, obviously you guys are the brokers trying to enable the apps, and we're the ones trying to provide data access in the easiest fashion, right? So, first a quick overview of what you're going to be looking at when you're harnessing the cloud, right? The two main things that we're talking about are scalability and agility. Those are the things that are most attractive about the cloud, right? You got massive quantities of elastic compute that you can utilize, which is ideal for like your HPC or your high performance computing applications. So, getting your app up there is one thing, but then, you have this concept of unlimited storage capacity in the cloud. There are some challenges with that and utilizing that and leveraging that to your benefit. You have software-defined networking, which allows you to grow your compute infrastructure and shrink it down and have to really not worry about network configuration, IP address assignment, all these other things that would typically be a difficulty in a data center environment. And then you have like multiple cloud providers and multiple region zones that allow you to take your application, spread it across different cloud service providers, spread it across different zones, availability zones, regions, whatnot, and really how do you benefit from all of that? Agility is the huge thing also, right? A lot of people run in-house compute and they want to use the cloud for burst computing or excess compute capacity that they're looking for. The benefits there, you can use APIs to rapidly deploy. You guys tie into that beautifully at Cycle Computing. Pay for compute as you go. So you really want to spin things up, do what you got to do, and spin things back down as quick as possible to get the bang for the buck that you're looking for. And growing and shrinking your infrastructure on demand is a really, really huge benefit of the cloud. You may start out with 100 instances or 1,000 instances, and then you might realize, well, I need to double that, triple that, 10 times. And being able to do that all programmatically and on demand is a huge deal. And then the last piece is picking and choosing your cloud providers. And I'll talk a little bit about each one of these in the coming slides. But what we really want to talk about are the challenges, because everybody understands kind of what the cloud is and what it can do for you, but no one really understands what kind of roadblocks and what kind of challenges you're going to encounter when you're actually moving your app up in there, right? So getting your app to run in the cloud, that's one thing, right? You have some platform integration work to do. You have, perhaps, some tweaks and tunings that you do to your application stack, depending on which operating system it's going to run inside of the cloud. But getting that solved is just one layer of complexity, and then you got a lot more to look forward to as you start to peel that onion back. Then you have like a grid engine, right? You have some sort of a grid management system that's going to dispatch jobs to all your compute nodes, right? Once you've got your application up there and running it, how do you manage hundreds or thousands of compute instances that are all somehow exchanging information and running work that is going to eventually result in the output that you're going to leverage from a productivity standpoint. So then you got stuff like network integration, you have network connectivity across your nodes, perhaps you're using different regions, availability zones, you have VPNs that are stretching between all these different areas, and these are all complexities that you're going to face. The big one is really transferring data between on-premises and the cloud. That's something that Avere can help with, but it's also just one small piece of the pie. You have like this data inertia, right? You don't want to move any more data than you actually require for your job to run. Time and quantity, these are all things that are going to affect how long you're in the cloud, how long you have your instances running for, and how you're able to get in and get out as quickly as possible. Once you've got your data in the cloud, now you got to figure out, well, how do I feed my application, right? So I got the data maybe stored in objects. How do I teach my application that was running in my data center against a file-based interface to access those objects, right? So that becomes a complicated thing and something that you have to solve for, right? So file interface compatibility for the sake of your application is also a big thing, right? Not a lot of cloud service providers have a solution that's readily available to fit that problem set. And then obviously the last piece is after you've run your compute job and you've done all this massive compute work and you've generated some output and some results, what do you do with those? Where do you store them? How do you haul them back on premises perhaps for your on-prem users to consume? So then data version management becomes an issue too, because some people choose, well maybe I'll just replicate my 5 terabyte data set into the cloud, and then I'm crunching on that, but maybe in the meantime someone made a change to 100 gig of that 5 terabyte, and how do you then find and isolate that 100 terabytes to change and resync that over? Yeah, there are tools out there that can do that, but they're not necessarily the most effective and efficient at that. So these are all kind of like the high-level challenges that you can expect beyond just securing your cloud compute resources and spinning up your application in the cloud. So just to get an idea for those that are not terribly familiar with kind of what the building blocks are for both on-prem and cloud, at Avere we like to use this diagram because it pretty much illustrates the landscape. On the top half you have the cloud, and on the bottom half you have your on-prem. Top left you have your cloud compute, which is essentially your Amazon EC2 instance, your Google Compute Engine, your Azure Compute. On the upper right-hand corner, you have cloud storage, which is object-based storage, which typically has an unlimited bottomless pit of capacity that you can just chuck objects in there all day long, and then you have to teach your application how to read and write those objects. On the bottom half is your typical data center infrastructure. On the bottom right, you have your on-prem storage. That's typically NAS, object. Some people have some block storage in there, but typically you need some software running on top of block to make it usable for more than one host. So I left block storage out there purposefully. And then you have your on-prem compute, which will consist of a grid and some desktop users, right? Everything is driven by humans in the end, but a lot of the work is done by the compute grid itself. So when you're looking at this infrastructure here, you're obviously faced with the challenge of how do you bridge the gap between on-prem and cloud, right? So there's a lot of network solutions out there, network technologies, 10 gig links, multi-10 gig links, file transfer protocols that really speed things up and fill the pipe, and all these technologies that help you solve some of the challenges with transferring data back and forth. But even once you've transferred data back and forth, you come to the realization that you want to do that as little as possible, right? Because data's heavy, it's painful to move, and once you move it, you don't want to move it again. Here, the other big things that you have to talk about are these applications here are typically data center applications. They might have been around, they might be around for 10, 15 years maybe, or maybe they're just recent applications. But in general, most people write an application to open a file, read some data from it, open another file to write the results out, and then they coordinate this across hundreds, if not thousands, of compute instances. Cloud storage doesn't really, you can't have hundreds of clients here all updating the same object in the cloud because you typically can't really do range updates of objects in the cloud. So file system, POSIX compliant file system allows you to have a shared model where a bunch of different writers are all contributing little bits and pieces to a file. That already is something that a lot of these compute grid type applications rely on. Or perhaps you have a shared directory where you have each host creating its own file, and then you have some post process that's going to collect all these files together and do that. So these are all storage problems that have to be solved in one way or another, and there's 100 different ways to skin this cat. But more importantly, what we can talk about is how Avere can enable this. So this is the same exact diagram, but what we'll talk about here is initially, Avere makes these orange boxes here. And the orange boxes are what we call the physical FXT clusters. These will sit on-prem. What these allow you to do is to leverage cloud storage, so object-based storage, and present a file system out to your clients. So typically, customers are going with these object-based storage systems because you can pay as you go, you can achieve massive scalability, high density, low power requirements, data protection through erasure coding, and all these great technologies that are there. But the one piece that's really missing is the file to object conversion, right? It's a gateway functionality. So Avere's core technology integrated this file system caching that we can do with the ability to transfer or to convert those operations into gets and puts that are actually going to be stored in the object storage while still maintaining these POSIX compliant file system operations up front. So what does that mean for the average user? It means that they don't have to retrain their applications to talk directly to the cloud storage. They can drop our technology in place. Additionally, if you're dealing with, let's say, public cloud storage vendors, you got this bandwidth and latency issue between your on-prem and your cloud. So you want to avoid traversing that as often as possible, which is where caching and coalescing of data makes a lot of sense at the edge as close as possible to your compute. The other ability that we have is to basically tie together all these different technologies of storage so that your application can actually read and write files and not have to be aware of all the different pieces of technology that are available. The virtual FXT is the piece that matters the most to customers of Cycle Computing, which means we have our software running inside of the cloud, which allows you to run your application here in the virtual compute farm against our appliance our software appliance running here, and it allows you to pick and choose. Am I going to store my data in the cloud? Am I going to store my data on-prem? Am I going to somehow maybe replicate my data for DR purposes into the cloud? Or am I going to move my data from on-prem into the cloud because I don't want to consume my on-prem resources to that extent? Or just, do I want to leverage all 4 quadrants of this simultaneously so that my application can maybe start on-prem and grow into the cloud, scale up, scale down, go back on-prem? The global namespace functionalities and the ability to address all of these different storage technologies really becomes a benefit there. So, typical scenario, we have customers that are doing life sciences stuff like the Broad. We have customers that are doing financial analytics. We have customers that are doing computer graphics rendering. These are all very computational and I/O intensive processes, right? But in the end, most of them keep all their data here, with the exception, some of the more cutting edge, like life sciences, next generation sequencing stuff. Now they're starting to live in the cloud and keep stuff in the cloud a little bit more for the collaboration models and whatnot. But in reality, most people are going to want to maintain the core of their data mining stuff on premises here. So what you can do, you can leverage spin up. Maybe let's say you start off with a few instances here running in your compute farm, and they can mount this system which is caching data that is stored on premises here. So maybe some user writes some job configuration or job description file to the storage which says, oh, I want to take 100 nodes in the cloud and start computing on some stuff. That gets stored here, and then when you fire up those 100 nodes in the cloud, they're going to go looking for their configuration file, and this system can pick up that file immediately, and then they start reading the files that their job is requiring them to do. This guy doesn't really know what they're asking for until they're asking for it, so they ask for their data, and we have techniques to essentially fill the pipe and prefetch and pull directory metadata and file system metadata and all the different blocks of the files that are being read into this cache here. And here it's stored in the local block storage of the cloud subsystem. And as clients are reading this data, instead of having to traverse all the way down here to get to that data, it's actually serviced right here, right in between the virtual FXT and the compute farm. So what does that mean? That means that you can now scale this system up, and as you scale the number of compute nodes that you're running, you're going to require more storage resources, more IOPS, more throughput, more reads, more writes, more directory lookups, all those things that would typically limit the amount that you can grow this infrastructure by. So our system here is also clustered, and it's scalable. So you start adding these virtual nodes to the system, and they spread out resources across all of them, and you don't really have to update any config files here, you don't have to change path names here. Everything that was running here can basically run here in just the same manner because you can virtualize all of this storage to be presented up into the cloud. And what that means in the end is that you can basically tear all of this down once you're done, and all your results that were written out get pushed back to your NAS here, and everybody that was typically used to accessing that data is able to now continue their work without even really realizing that the compute cloud was actually leveraged to generate those results. So in the end, Cycle Computing enables customers to scale this workload, and we're the enablers of getting this workload up into the cloud and back with minimal changes. And in the end, that's really where the agility and the scalability comes in, and that's how you get the most bang for your buck while you're working up in the cloud. So I think, if you guys have any questions, I'd be love to address them, but typically this is kind of like the high level pitch. I'm a very technical guy, so if you guys have technical questions, feel free to fire away, or if you have any other comments, feel free.